Constructors with care. Constructors are special functions that often perform critical, privileged tasks when initializing contracts. Before Solidity version 0.4.22, constructors were defined as functions that had the same name as the contract that contained them. In such cases, when the contract name is changed in development, if the constructor name isn't changed too, it becomes a normal, callable function. As you can imagine, this can lead to some interesting contract tags. For further insight, the reader may be interested in attempting the Etherknot challenges, in particular the Fallout level. The vulnerability. If the contract name is modified, or there is a typo in the constructor's name such that it does not match the name of the contract, the constructor will behave like a normal function. This can lead to dire consequences, especially if the constructor performs privileged operations. Consider the following contract. Contract owner wallet, open brace, address public owner. Code comments, constructor. Function, lowercase owner wallets, with one parameter, address underscore owner. Public, open brace, owner equals underscore owner. Close brace. Code comments, fallback, collect ether. Function with no parameters, payable, open brace, close brace. Function withdraw with no parameter, public, open brace, require message.sender equals owner. Message.sender.transfer invoked with this.balance. Close brace, close brace. This contract collects ether and allows only the owner to withdraw it by calling the withdraw function. The issue arises because the constructor is not named exactly the same as the contract. The first letter is different. Thus, any user can call the owner wallet's function, set themselves as the owner, and then take all the ether in the contract by calling withdraw. Preventative techniques. This issue has been addressed in version 0.4.22 of the Solidity compiler. This version introduced a constructor keyword that specifies the constructor, rather than requiring the name of the function to match the contract name. Using this keyword to specify constructors is recommended to prevent naming issues. Real-world example, Rubixi. Rubixi was another pyramid scheme that exhibited this kind of vulnerability. It was originally called Dynamic Pyramid, but the contract name was changed before deployments to Rubixi. The constructor's name wasn't changed, allowing any user to become the creator. Some interesting discussion related to this bug can be found in Bitcoin Talk. Ultimately, it allowed users to fight for creator status to claim the fees from the pyramid scheme. More details on this particular bug can be found in History of Ethereum Security Vulnerabilities, Hacks, and Their Fixes. Uninitialized storage pointers. The EVM stores data either as storage or as memory. Understanding exactly how this is done and the default types for local variables of functions is highly recommended when developing contracts. This is because it is possible to produce vulnerable contracts by inappropriately initializing variables. To read more about storage and memory in EVM, see the Solidity documentation on data location, layout of state variables in storage, and layout in memory. Note: this section is based on an excellent post by Stephen Bayer. Further reading on this topic inspired by Stephen can be found in this Reddit thread. The vulnerability. Local variables within functions default to storage or memory depending on their type. Uninitialized local storage variables may contain the value of other storage variables in the contract. This fact can cause unintentional vulnerabilities or be exploited deliberately. Let's consider the relatively simple name registrar contract in nameregistrar.sol. Code comments. A locked name registrar. Contract, name registrar, open brace. Boolean public unlocked equals false. Code comment, registrar locked no name updates. Struct name record open brace code comment map hashes to addresses. Bytes 32 name address mapped address close brace. Code comment records who registered names. Mapping from address to name record public registered name record. Code comment resolves hashes to addresses. Mapping from bytes 32 to address public resolve. Function register with two parameters bytes underscore name and address underscore mapped address. Public open brace code comment set up the new name record. Name record new record. New record.name equals underscore name. New record.map address equals underscore mapped address. Resolve of underscore name equals underscore mapped address. Registered name record of message.sender equals new record. Require unlocked. Code comment only allow registrations if contract is unlocked. Close brace. Close brace. This simple name registrar has only one function. When the contract is unlocked, it allows anyone to register a name as a bytes 32 hash and map that name to an address. The registrar is initially locked, and the require online 25 prevents register from adding name records. It seems that contract is unusable, as there is no way to unlock the registry. There is, however, a vulnerability that allows name registration regardless of the unlocked variable. To discuss this vulnerability, first we need to understand how storage works in Solidity. As a high-level overview, state variables are stored sequentially in slots as they appear in the contract. Thus, unlocked exists in slot 0, registered name record in slot 1, and resolved in slot 2. Each of these slots is 32 bytes in size. There are added complexities with mappings, which we will ignore for now. The Boolean unlocked will look like 0x0 for false, or 0x0 for true. As you can see, there is a significant waste of storage in this particular example. The next piece of the puzzle is that Solidity by default puts complex data types such as structs in storage when initializing them as local variables. Therefore, new record on line 18 defaults to storage. The vulnerability is caused by the fact that new record is not initialized. Because it defaults to storage, it is mapped to storage slot 0, which currently contains a pointer to unlock. Notice that on line 19 and 20, we then set new record.name to underscore name and new record.mapped address to mapped address. This updates the storage location of slot 0 and slot 1, which modifies both unlock and the storage slot associated with registered name record. This means that unlock can be directly modified simply by the bytes underscore name parameter of the register function. Therefore, if the last byte of underscore name is non-zero, it will modify the last byte of storage slot 0 and directly change unlocked to true. Such underscore name values will cause the required call on line 25 to succeed, as we have set unlocked to true. Try this in Remix. Note that the function will pass if you use a underscore name of the form 0x0 Preventative Techniques. The Solidity compiler shows a warning of uninitialized storage variables. Developers should pay careful attention to these warnings when building smart contracts. The current version of MIST 0.10 doesn't allow these contracts to be compiled. It is often good practice to explicitly use the memory or storage specifiers when dealing with complex types to ensure they behave as expected. Real-world examples: Open Address Lottery and Crypto Roulette's honeypots. A honeypot named Open Address Lottery was deployed that used this uninitialized storage variable quirk to collect Ether from some would-be hackers. The contract is rather involved. So we will leave the analysis to the Reddit thread where the attack is quite clearly explained. Another honeypot, Crypto Roulette, also utilized this trick to try and collect some ether. If you can't figure out how the attack works, see an analysis of a couple Ethereum honeypot contracts for an overview of this contract and others. Floating point and precision. As of this writing, version 0.4.24, Solidity does not support fixed point and floating point numbers. This means that floating point representations must be constructed with integer types in Solidity. This can lead to errors and vulnerabilities if not implemented correctly. Note: for further reading, see the Ethereum Contract Security Techniques and Tips wiki. The vulnerability. As there is no fixed point type in Solidity, developers are required to implement their own using the standard integer data types. There are a number of pitfalls developers can run into during this process. We will try to highlight some of these in this section. Let's begin with a code example. We will ignore under and overflow issues discussed earlier in this chapter for simplicity. Contract, fun with numbers, open brace. uint constant public, tokens per ETH equals 10. uint constant public, way per ETH equals 1 E18. Mapping from address to uint public balances. Function, buy tokens with no parameters, external payable, open brace, code comment, convert way to ETH, then multiply by token rates. uint tokens equals message.value divided by way per ETH times tokens per ETH. Balances of message.sender incremented by tokens. Close brace. Function sell tokens with one parameter, uint tokens, public, open brace, require balances of message.sender greater than or equal to tokens. uint ETH equals tokens divided by tokens per ETH. Balances of message.sender decremented by tokens. Message.sender.transfer of ETH.way per ETH. Close brace. Close brace. This simple token buying/selling contract has some obvious problems. Although the mathematical calculations for buying and selling tokens are correct, the lack of floating point numbers will give erroneous results. For example, when buying tokens on line 8, if the value is less than 1 ether, the initial division will result in 0, leaving the result of the final multiplication as 0. For example, 200 way divided by 1 E18 way per ETH equals 0. Similarly, when selling tokens, any number of tokens less than 10 will also result in 0 ether. In fact, rounding here is always down, so selling 29 tokens will result in 2 ether. The issue with this contract is that the precision is only to the nearest ether, in other words, 1 E18 way. This can get tricky when dealing with decimals in ERC20 tokens when you need higher precision. Preventative techniques. Keeping the right precision in your smart contracts is very important, especially when dealing with ratios and rates that reflect economic decisions. You should ensure any ratios or rates you're using allow for large numerators in fractions. For example, we used the rates tokens per ETH in our example. It would have been better to use way per tokens, which would be a large number. To calculate the corresponding number of tokens, we could do message.value divided by way per tokens. This would give a more precise result. Another tactic to keep in mind is to be mindful of order of operations. In our example, the calculation to purchase tokens was message.value divided by way per ETH times token per ETH. Notice that the division occurs before the multiplication. Solidity, unlike some languages, guarantees to perform operations in the order in which they are written. This example would have achieved a greater precision if the calculation performed the multiplication first and then the division. In other words, message.value times token per ETH over Wei per ETH. Finally, when defining arbitrary precision for numbers, it can be a good idea to convert values to higher precision, perform all mathematical operations, then finally convert back down to the precision required for output. Typically, uint256 are used as they are optimal for gas usage. These give approximately 60 orders of magnitude in their range, some of which can be dedicated to the precision of mathematical operations. It may be the case that it is better to keep all variables in high precision in Solidity and convert back to lower precisions in external apps. This is essentially how the decimals variable works in ERC20 token contracts. To see an example of how this can be done, we recommend looking at ds-math. It uses some funky naming, but the concept is useful. Real-world example, ETH stake. The ETH stake contract does not use extended precision. However, it deals with Wei. So this contract will have issues of rounding, but only at the Wei level of precision. It has some serious flaws, but these relate back to the difficulty in getting entropy on the blockchain. For a further discussion of the ETH stake contract, we will refer you to another post by Peter Vasinis. Ethereum contracts are going to be candy for hackers. Transaction.origin authentication. Solidity has a global variable, transaction.origin, which traverses the entire call stack and contains the address of the account that originally sent the call or transaction. Using this variable for authentication in a smart contract leaves the contract vulnerable to a phishing-like attack. Note: for further reading, see D. Bryson's Ethereum Stack Exchange question, Transaction.origin and Ethereum Oh My, by Peter Vasinis, and Solidity Transaction Origin Attacks by Chris Coverdale. The vulnerability. Contracts that authorize users using the transaction.origin variable are typically vulnerable to phishing attacks that can trick users into performing authenticated actions on the vulnerable contract. Consider the simple contract in phishable.sol. Contract phishable open brace address public owner constructor with one parameter address underscore owner open brace owner equals underscore owner close brace function with no parameter external payable open brace close brace function withdraw all with one parameter address underscore recipients public open brace require transaction.origin equals owner underscore recipients dot transfer invoked with this dot balance close brace close brace. Notice that on line 11 the contract authorizes the withdraw all function using transaction.origin. This contract allows for an attacker to create an attacking contract of the form import phishable.sol contract attack contract open brace phishable contract address attacker constructor with two parameters phishable underscore phishable contract and address underscore attacker address phishable contract equals underscore phishable contract attacker equals underscore attacker address close brace function with no parameters payable open brace phishable contracts dot withdraw all invoked with attacker close brace close brace. The attacker might disguise this contract as their own private address and socially engineer the victim, the owner of the phishable contract, to send some form of transaction to the address, perhaps sending this contract some amount of ether. The victim, unless careful, may not notice there is code at the attacker's address, or the attacker might pass it off as being a multi-signature wallet or some advanced storage wallet. Remember that the source code of public contracts is not available by default. In any case, if the victim sends a transaction with enough gas to the attack contract address, it will invoke the fallback function, which in turn calls the withdraw all function of the phishable contract with the parameter attacker. This will result in the withdrawal of all funds from the phishable contract to the attacker address. This is because the address that first initialized the call was the victim, in other words, the owner of the phishable contract. Therefore, transaction.origin will be equal to owner, and the require on line 11 of the phishable contract will pass. Preventative techniques. Transaction.origin should not be used for authorization in smart contracts. This isn't to say that the transaction.origin variable should never be used. It does have some legitimate use cases in smart contracts. For example, if one wants to deny external contracts from calling the current contract, one could implement a require of the form require transaction.origin equals message.sender. This prevents intermediate contracts being used to call the current contract, limiting the contracts to regular code list addresses. Contract libraries. There is a lot of existing code available for reuse, both deployed on-chain as callable libraries and off-chain as code template libraries. On-platform libraries have been deployed, exist as bytecode smart contracts, so great care should be taken before using them in production. However, using well-established existing on-platform libraries comes with many advantages, such as being able to benefit from the latest upgrades, and saves you money and benefits the Ethereum ecosystem by reducing the total number of live contracts in Ethereum. In Ethereum, the most widely used resource is the Open Zeppelin suite, an ample library of contracts ranging from implementations of ERC20 and ERC721 tokens, to many flavors of crowd sale models, to simple behaviors commonly found in contracts, such as ownable, possible, or limits balance. The contracts in this repository has been extensively tested and in some cases even function as de facto standard implementations. They are free to use and are built and maintained by Zeppelin together with an ever-growing list of external contributors. Also from Zeppelin is Zeppelin OS, an open-source platform of services and tools to develop and manage smart contract applications securely. Zeppelin OS provides a layer on top of the EVM that makes it easy for developers to launch upgradable dApps linked to an on-chain library of well-tested contracts that are themselves upgradable. Different versions of these libraries can coexist on the Ethereum platform, and a vouching system allows users to propose or push improvements in different directions. A set of off-chain tools to debug, test, deploy, and monitor decentralized applications is also provided by the platform. The project ETHPM aims to organize the various resources that are developing in the ecosystem by providing a package management system. As such, their registry provides some more examples for you to browse. Conclusions. There is a lot for any developer working in the smart contract domain to know and understand. By following best practices in your smart contract design and code writing, you will avoid many severe pitfalls and traps. Perhaps the most fundamental software security principle is to maximize reuse of trust code. In cryptography, this is so important it has been condensed into an adage: don't roll your own crypto. In the case of smart contracts, this amounts to gaining as much as possible from freely available libraries that have been thoroughly vetted by the community.